Hello, my name is Chris Winslow. I'm the Interim Director for the Ohio Sea Grant College Program and Ohio State University Stone Laboratory. I want to take this opportunity over the next 15 minutes to talk to you about some of the critical information that Ohio Sea Grant and OSU feel needs to be out into the stakeholders' hands related to harmful algal blooms. So for a quick reference of where I'm going to go, so I really want to highlight the economic importance of Lake Erie. I want to talk about blooms in the context of climate change. We need to all know that spring rains are the key to these blooms, or one of the key roles or key players in how severe these blooms are. I want to make sure individuals understand the difference between TP, which is total phosphorus, and DRP, which is dissolved reactive phosphorus. And I want to show you some trends through time in Lake Erie. I want to talk to you about the difference between phosphorus loading and phosphorus concentrations, and this is a critically important, there's a critical important difference between these two things. I want to talk about the fact that there are many sources for phosphorus, but we do know that ag is one of the major players. Upwards of 65% of the phosphorus contributed in the spring or annually comes from agricultural activities. And then at the end, I want to just kind of wrap up some Board of Regents highlights. So again, the Board of Regents is funding $2 million worth of research in Lake Erie related to harmful algal blooms, and I wanted to briefly discuss some of those projects, or at least the general context or the general questions that are being addressed. So first off, again, the economic importance of tourism in Lake Erie region. Basically, I want to be able to draw your attention to the red outlined regions. So those are the 8 counties that border Lake Erie. Within these 8 counties, sales is at a level of $2.9 billion. Wages earned related to tourism in these 8 counties is at $3.3 billion. Tax revenue, this is federal, state, and local taxes, bring in about $1.7 billion to those 8 counties, and about 119,000 individuals are employed by that tourism sector. That works out to about 1 in every 12 individuals within these counties has a job related to tourism. And this is just one line of evidence that highlights the economic importance of tourism in the Lake Erie region. And so this is something that we as a program, Ohio Sea Grant and OSU Stone Laboratory, always highlight, that this is a critically important region for the state. Of the roughly $40 billion in tourism revenue for the state, as I mentioned, $12.9 billion of that comes from only 8 of 88 counties. The next thing I want to transition to, and this is basically a land use map of the watershed of the Great Lakes, but specifically if you look at Lake Erie, it's surrounded by a lot of reds, yellows, and oranges. And if you look at the key, the driving point I want to make with this slide is that we are surrounded by a lot of urban areas, so people, also different degrees of farming or farming and pasture use. So those are the orange and yellow colors. If you actually break this down into a graph, which has percent of land coverage on the vertical axis or the y-axis, the lakes are along the x-axis, you'll see in the orange color that we're first in residential land use. So we have the most people in our watershed relative to the other 4 Great Lakes. We're first in cropland relative to the other 4 Great Lakes. We're only second in pasture, falling behind Ontario. We have the least amount of forested area, which is the yellow shaded region relative to the other 4 Great Lakes. And I have the number 10% within the red bar. That bar represents wetlands. As you can see, Lake Michigan and Lake Huron both have more wetlands than Lake Erie has, but I put 10% there to remind individuals that we only have about 10% of historic wetlands that exist. So about 90% have been converted to some other land use. And this really graph, and I know that individuals that will access this webinar or this PowerPoint have probably heard this information before, but I want to make sure it's out there because what it can allow us to say is that Lake Erie gets more sediment and nutrients than all the other Great Lakes. And when I say nutrients, I'm referring to commercial fertilizers and manure because of the heavy agricultural use in its watershed, but also sewage because of the heavy population within the watershed. And I also want to move into my second point that I put on the outline slide, which is the fact that these harmful algal blooms are exacerbated and these nutrient loads are exacerbated by storms. And what we are seeing is more frequent storming events, but also more severe storm events. So events that are larger in size, so as far as the volume of water drop during these events. I also want to remind individuals that are looking at this PowerPoint or listening to this webinar that Lake Erie is the shallowest of the 5 Great Lakes. And so these inputs into this water body are going to elevate concentrations in a pretty small water body relative to the other Great Lakes. But as a result, with the graph I showed you previously showing, again, land use, and I'll give you a glimpse back at that graph, we can clearly show that Lake Erie is going to be the most productive of the Great Lakes. And oftentimes this program has emphasized what we call the 50-to-2 rule. So Lake Superior has about 50% of the Great Lakes water, Lake Erie has about 2%, but Lake Erie has about 50% of the biomass of fish relative to Lake Superior, which has only about 2% of the biomass. So this is a very, very, very productive system. That in itself is not a bad thing. This is why we're the walleye capital of the world, because we have a lot of we have nutrient inputs that give us algal growth, and that algal growth is the base of the food web that supports a lot of life. But in any talk I give related to Lake Erie and nutrient loading and harmful algal blooms is that we can always have too much of a good thing. Some nutrients are good. Having a productive lake is a good thing. But when we push that too far and throw the ecological balance off, that's the concern we have. So the next point I wanted to move into was this taking HABs and nutrient loading in the context of climate change. We need to know, and this is a busy slide, and I don't have the ability to animate some of this, but what I really want to show that we're seeing an increase in, again, the volume of water that's dropped in these rain events, but also the frequency of these rain events. So if you look at the first sub-bullet, the number of storm runoff events per year is up about 67% from the time period of 1960 to 2010. More importantly, I would argue, is that the second sub-bullet says the number of spring runoff events is up 40%. This is critically important because it's that spring period that is going to be responsible for delivering the nutrients that ultimately drive these blooms. The last one I want to show you also is that the annual storm discharge, the fourth sub-bullet, is up 53%. Again, highlighting this data coming from Heidelberg and Dr. Pete Richards, highlighting that these storm events are not only more frequent, but they're larger in size. Okay. The other seasonal comparisons that were done that aren't on this slide also are showing increases, but not significant increases. So what this illustrates to us, the punchline you should take from this slide right here is that 80 to 90% of the loading happens 10 to 20% of the time. So these heavy storm events, these 10 to 20% of the storm events that happen are carrying the vast majority of nutrient loading, and that's primarily phosphorus into the lake. This graph also shows that same thing, and I want to walk you through each of these panels. Starting on the left, this one on the y-axis shows spring discharge. This is for the Maumee River, and on the bottom axis is date through time. And what you'll see is the gray represents the range from 2011 through 2015, and then each individual line color represents a different year. And what you'll see is the black line represents the mean. And what it's showing you is the mean discharge across all these years. On the panel to the right, you're seeing DRP, and remember that stands for dissolved reactive phosphorus. Same kind of scenario with what you're looking at. Gray is the range, the different lines represent the different years. But what I want to highlight is when you look at a vertical increase, like let's follow the green line for 2011 in the panel on the left, when you see that increased discharge, that heavy storm that happens in that early March period, you will also see a corresponding phosphorus load. And then you'll see in flatline areas where there is low discharge, you'll see low phosphorus inputs. So what I really want you to recognize in the take-home message from this slide, and again in the context of climate change, is that when you get these storm events, those discharge events are correlated with these high dissolved reactive phosphorus concentrations. Okay? I'm just showing you a figure of some of these blooms in the basin. So this is a photo from September 24th of 2013, showing you the green bloom there in the Western Basin. The next slide is giving you a look into the severity of these blooms over the last 13 years, from 2002 to 2014. Warm colors, meaning the orange and reds, are high concentrations of blooms, where the cool colors, the purples and the blues, are lower concentrations. Black means no bloom present. I show you this across the year because you'll see that from 2008 to 2014, we're seeing quite a bloom footprint in the Western Basin and in some cases in the Central Basin of Lake Erie. Moving more closely, I want to take a close-up view of 2008, which was a heavy precipitation year, and I want to compare that to 2011, which was one of our worst blooms on record, and 2012, which was one of our smaller blooms on record. And so what you're seeing on this slide is those images pulled out, 2008 on the top, 2011, the worst bloom on record in the middle, and 2012, what we would call a moderate or minimal bloom. And what I want to do, and again, this is a busy slide, what I want you to be able to recognize is how this is driven by spring rains. So if you look at 2008, the peculiar thing about 2008 is this was a very wet year. If you look at discharge, so the amount of water coming through this system, we had 8 billion cubic meters in this year. So that's high relative to 11, worst bloom on record, and 12, a weak bloom, where those only had about 6.2 billion or 6.1 billion cubic meters of annual discharge. What you'll see is the big difference across these, for one that had a heavy bloom in 2011 versus a moderate bloom in 2012, is that spring discharge. So you'll see in 2008, the spring discharge was 3.4 billion cubic meters, where in 2011, it was 5 billion cubic meters. So of that 6.2 billion that fell into the lake during 2011, the bulk of it, the lion's share, came in the spring. Versus 2012, which again had a comparable annual discharge, 6.1 to 6.2, to the 2011 year, but look at the spring discharge, only 1 billion cubic meters in the spring. And so what that does is it changes the loading happening in that spring period. So you'll see in 2008, our reference year, we had about 3.4 billion of spring discharge, and the spring load of phosphorus was 1,400 metric tons. And you can see the resulting bloom. But look in 2011, the worst bloom on record, when you have that 5 billion cubic meters of spring discharge, the spring load is 2,300 tons. So that's where that bloom is being driven from. In opposition to that, or in contrast to that, in 2012, if you look at the spring load, again, the discharge was 1 billion cubic meters, but the spring load was only 400 tons. Not enough phosphorus in that spring period to tie into a bloom. So two things we can wrap together here. One is that if you get heavy rain events and more frequent rain events, you're going to load those nutrients. But the timing of that nutrient input, the spring, is critically important. In 2011, we had a heavy spring discharge and a heavy spring load, resulting in a heavy bloom. In 2012, we had a low spring discharge and a low spring load of phosphorus, and there was a minimal bloom. I want to definitely talk about the difference between TP, which is total phosphorus, and DRP, which is dissolved reactive phosphorus. Total phosphorus is a measure of all, as the name suggests, all the phosphorus in the water. And what you'll see is that only about 25 to 50% of that phosphorus is actually readily available to those blooms. If you look at the graph I've given you, we're measuring total phosphorus on the vertical axis and time on the x-axis. What you'll see, the line that breaks through this graph shows that there is an increase, but it's only about a 13% increase in total phosphorus from 1990 to roughly present day. Okay? But if you take this and compare it to DRP, which is the phosphorus that's more readily available to blooms, we're seeing a 144% increase. So we're seeing this from 1990 to 2012, a dramatic increase in the amount of DRP. Again, phosphorus that's readily available to blooms and the cyanobacteria. What this has shown us is that what we're really working on now is how do we address this DRP? And we've shown from multiple studies that most of this DRP, or a lot, I wouldn't say most, but a lot of this DRP is coming from drain tiles coming off of agricultural fields. We've seen studies that show anywhere from 40 to 50% of the phosphorus entering those rivers is coming directly from drainage tiles. So there is a difference. Total phosphorus is all the phosphorus in the system. DRP is that's available, readily available for the cyanobacteria or harmful algal blooms, and that has shown a dramatic 144% increase since 1990. This slide I'm using to talk to you about the difference, and this is key, the difference between phosphorus loading, okay, the amount of total phosphorus entering the system, total phosphorus we're talking, versus concentration, okay? Total phosphorus load is important, and that's what all the models use to predict these blooms. But what you're seeing on this graph, and this data is from 2008, it's one of the years that we have the most comprehensive data available, you're seeing a dot or a bar on all the major tributaries of the Great Lakes. Dots mean they're tributaries that are less than 100 metric tons annually, and bars are those that are above 100 metric tons annually. And the value is placed next to those dots and the bars. What you'll see is the Maumee River down here above the box that says 80-10-10, and this year has 3,800 and change metric tons of phosphorus added to the western basin of Lake Erie. Excuse me. Oftentimes individuals talk about how Detroit River is playing, or they suggest that the Detroit River is playing a role in these blooms or causing these blooms. Well, you can see that Detroit is providing a lot of total phosphorus. In this case, in 2008, 2,040 metric tons annually of total phosphorus. The difference I want to drive home here, again, the difference between loading and concentration draws us to that yellow box in the bottom, 80-10-10. Again, this is a rule that Ohio Sea Grant and OSU Stone Laboratory mention all the time. What this shows you is where the water into Lake Erie comes from. 80% of it comes from the Detroit River, 10% from all the tribs outside the Detroit River, and 10% from precipitation directly on the lake. So what this is telling you is that 2,000 metric tons, approximately 2,000 metric tons, that are coming from the Detroit River are coming from the same place that the bulk of the water is coming from, where the Maumee River, bringing 3,800 metric tons, is coming in a much smaller volume of water. And therefore, the concentration is that in which we can drive a bloom. The concentration coming out of the Detroit, although it's a high, again, total phosphorus load, is diluted to the portion where it can add to the bloom severity, but it's not driving the onset of that bloom. Same thing is being shown from this. Again, a very busy graph. Wasn't able to use animations in this, but basically on the top 4 panels, you're seeing 2008 total phosphorus, 2011, 12, and 13 total phosphorus. It's broken down into red is the Detroit River contribution, blue is the Maumee River concentration, and then, contribution, and green is all the other tribs outside the Detroit and Maumee. What you'll see is that depending on the year, it hovers between about 45% or high 30% of contribution from Detroit versus the Maumee River. But again, and then we can pull that down to the bottom left-hand corner, that's an average across 2011, 2012, 2013. So the bottom left-hand corner, that's the average of total phosphorus contributed from the Detroit, the Maumee, and other tribs across 11, 12, and 13. You can see that it's about equal in the contribution of total phosphorus. However, if you look at the panel to the right, which shows flows through those rivers, you can see that 95% of the flow across those 3 years, 11, 12, and 13, came from the Detroit River, where only 4% came from the Maumee. And so what that tells you is that if you take the total phosphorus and do an average flow-weighted total phosphorus concentration, which is the bar graph to the right, the Maumee River is a tremendous input, as are the other rivers outside the Detroit River, bringing total phosphorus into the system. So again, we've got to distinguish between loading of total phosphorus versus concentrations. Okay? Yes, Detroit has a lot of phosphorus loading, as does the Maumee, but the flow coming out of the Detroit makes the concentrations in that river too low to be driving the blooms. Again, that phosphorus can contribute to the severity of that bloom, but they're not driving the onset and ultimately the scope of those blooms. Last thing I want to do to wrap out the 15 minutes that I had allocated to me was talk about some actions that we can take. And again, these have been disseminated by Ohio Sea Grant and OSU Stone Lab and OSU as a whole and many other institutions. But I definitely wanted to highlight these possible action areas. This whole slide you're looking at right now is agricultural actions. Again, I want to highlight that, again, the lion's share of that phosphorus being contributed to the system, anywhere from 65 to 80%, depending on how wet that spring is coming from agricultural practices. This is not, the intent of this is not to say that, it's all ag's fault and we're blaming agriculture for this. We're just identifying the sources, and now we need to work as a community of scientists and stakeholders to address the problem together. So really concentrate on the red bolded areas. So the first thing we can do is eliminate the application of fall and winter application of commercial fertilizers and manures. We'd like to eliminate broadcast application and do some incorporation of these different types of fertilizer into the soil. We'd like to get a more exhaustive and efficient soil testing in place. We are seeing that a lot of Ohio fields, in this case of roughly 30%, already have too much phosphorus present and don't need the addition of extra fertilizers or manure. We ask to continue no fertilizer application when the rain is forecasted within 48 hours. We'd like to at least place a moratorium on addition of tiles. We really need to get a handle on this contribution of dissolved reactive phosphorus coming from these drain tiles. Again, anywhere from 40 to 50% of the DRP, dissolved reactive phosphorus, is coming from these sources. And the last one is maybe consider reducing the size of farms falling under CAFO. CAFO are concentrated animal feeding operations. And basically the idea is, can we work on controlling manure inputs into the system by looking at the management of manure on these different size farms. Other levers we can pull outside of the agricultural realm, lawn care, so the application of fertilizer on our urban landscapes. So again, if we can be applying zero phosphorus fertilizers would be one way we can address the phosphorus input. Trying to reduce property runoff, whether this is through rain barrels or porous surfaces or rain gardens. Sewage treatment plant recommendations, not only eliminate combined sewer overflows or CSOs, but also try and reduce the volume that's sent to the treatment plants. This whole issue, harmful algal blooms, nutrient loading, we often hear it talked about as a nutrient problem. That is true. Phosphorus is driving these. We also need to think of this in terms of a water management issue also. So how do we maintain those more frequent and more severe storms on the landscape? Water treatment plant operations, so not sewage treatment, but water treatment. We do have a history of adding phosphate to treated water because it slows corrosion, possibly addressing that input of phosphorus. And then also there are septic tanks along Lake Erie and also inland. This harmful algal bloom issue isn't just a Lake Erie issue, but we can be more closely monitoring septic tanks. The last thing I want to do before I run over on time is to highlight the 5 focus areas of the $2 million that was provided by the Board of Regents to researchers throughout the state. Yes, Ohio Sea Grant and OSU Stone Lab is managing these projects and making sure the projects are being completed as outlined and the budgets are being spent properly. But this research is happening across 8 universities, across 18 different projects. Focus areas here are basically HABs detection and water quality. So we're looking with these projects to look at how we detect, map, and warn individuals of the presence of HABs. One is to produce safe drinking water. We know correcting and lowering the phosphorus input of the lake is not going to happen overnight, and this is a goal that we have to strive for over the next 5 to 10 years. But what we can do right now is arm those water treatment plants with tools, technologies, and training to get the toxins out of the water. We need to work on land practices, so edge of field monitoring and implementing BMPs throughout the Maumee River watershed and throughout the entire watershed, I would argue. Human health and toxicity. Again, even though the blooms might be here for a while until we get a hold on land use practices and sources of phosphorus, we need to worry about the health effects right now. So we're studying the presence of toxins in fish tissue and the impact of these toxins, for example, on liver. And the last thing is to look at the economic and policy levers we can pull to help get us to a place where we can reduce these phosphorus loads by 40%, over the next few years. And with that, I'm actually going to just show the fact again that this is not just a Lake Erie problem. These are some images of other lakes throughout the region, and just want to highlight the fact that this is an issue that we need to address and that we need to be working on. Any questions that you might have based on this presentation or this PowerPoint, feel free to contact Dr. Chris Winslow at Ohio Sea Grant, and I can address any questions you might have. Thank you for your time.